principles of estimation for MIMO or OFDM wireless communication. In this course, mainly we discuss about the wireless fading channel estimation of the mean and variance of the pilot training based on maximum likelihood. This is Karthik, Assistant Professor, Department of Electronics and Communication Engineering, Institute of Aeronautical Engineering, Hyderabad. Okay, coming to wireless fading channel estimation, in the previous session also we discussed likelihood. Okay, there also we find out the mean and variance. Okay, coming to in this session we discussed main about the mean and variance of the maximum likelihood. Okay, what is the difference between the previous session and this one? There we discussed the likelihood of the mean and variance. Coming to here, mainly we discuss about the this maximum likelihood estimation. Okay, what is that maximum likelihood means? Okay, this is we can maximize the likelihood function. Okay, then only the maximum likelihood estimation will come. Okay, we have to maximize the likelihood function, then we can give the process of the maximum likelihood estimation. Okay, here in this estimation we have to find out the parameters, and also we are taking the probability distribution by maximizing the likelihood function. Okay, then we can assume the some statistical models here. Okay, here for the observation purpose we are taking the one statistical model. Okay, in the previous sessions also we discussed about the statistical model. There we are taking the wireless sensor network. Okay, in the previously we are taking the wireless sensor network. Okay, in that wireless sensor network we are considering the one observation model. What is observation model? That is the node. We are considering the one node we are taking in the observation model. What is the observation here? We have to find out the unknown parameter, then it can add it by the noise. Okay, that we are already find out in the previous sessions. We are considering the one observation model, and also we are considering the multiple observation in the one particular cluster. Okay, in the cluster we are having the different nodes. There we are considering the one different multiple observations. For example, if you go for the one observation means y equal to h plus v. This is a one observation model. Okay, for that you are considering the multiple observation means y equal to y1 equal to h plus v1, y2 equal to h plus v2. Okay, like that, so on we are considering the up to n samples. Okay, here this is a multiple observation. In this one mainly we are considering the this is the unknown parameter. Okay, here the v1 to up to so on vn, these are the IID, independent identical distributions. Okay, those are the independent identical distributions. Here these are the observation parameter. These are the observation parameter. Okay, like that we have to considering the all statistical model. Those observation data is the most probable. Okay, whenever we need the maximum likelihood estimation, then we can maximize the likelihood function. Okay, in the previous session also we have taken the mean value 0 and sigma square is the variance. Okay, for that we are considering for the h value and estimation of the noise. There we also find out estimation of the noise value is the mean is 0, and estimation of the noise value in the variance, that is a sigma square. Okay, those already we find out in the maximum likelihood function. Same as here also we can find out the all the parameters in the maximum likelihood function. Okay, in this parameter, okay, the point of the parameter we have to take the space that maximize the likelihood function, that is called maximum likelihood estimation. Okay, this is called maximum likelihood function, but we have to estimate the parameters. What are the unknown parameters or known parameters in the observation model? We are considering the maximum likelihood estimation, that is here we can maximize the likelihood function, that is called maximum likelihood estimation. Okay, in this one mainly we are taking the one observation model. In the one observation model we are having the observation parameter, and also we are taking the unknown parameter, and also we can find out the variance. Okay, these are comes under the statistical model. Next, go to the some logic of the maximum likelihood is the both intuitive and flexible, and as such method become a dominant means of the statistical interference. There we can go with the maximum likelihood function, or also we can take in the likelihood function is a differentiable, and also we have to determine the maximum can be applied to that particular function. Okay, some of the case we are checking the first order conditions of the likelihood function. They be having the some solved explicitly, and also we taking the instance, and also we taking the ordinary least square estimator maximize the likelihood function in a linear regression model. Okay, for that we are taking the linear regression model. There we can use this particular functions in the likelihood function. Through these conditions or through these parameters, we have to estimate the maximum likelihood function. We have to maximize. Then only the function it is called maximum likelihood estimation. Then we can go with the some explicitly instance and ordinary least squares estimator. Okay, in the linear regression model. Okay, coming to coefficients in a wireless communication system. We know the wireless communication system. What is a coefficient? Here we having the channel coefficient. How we can justify the channel coefficient? That means we are considering the one transmitter and one receiver. We are considering the one transmitter, one receiver. We are considering the these one. Okay, in between we are having the medium or channel. We are having the medium or channel. Okay, this is the H. This is the H. That is a channel coefficient. Okay, what is the estimation of channel coefficient? Means we have to give the estimation of the channel coefficient. That is a H hat. That is a estimation of the channel coefficient. Here we having the different pilot symbols in the coming to transmitter side and coming to receiver side. We are having the two different pilot symbols. What is the two different pilot symbols? Coming to first one is the transmitted pilot symbols. Coming to here received pilot symbol. Coming to here on the transmission side we are having the transmitted pilot symbol. Coming to receiver side we are having the received pilot symbol. Okay, in between this is the channel coefficient. Okay, that here we can give the y equal to h x of k plus v. Okay, here this is the h is the channel coefficient, x of k is the transmitted pilot symbols, y is the output pilot symbol or observation parameters, v is the Gaussian noise. Okay, here v is the Gaussian noise. That h is represents the in that one channel coefficient, that and also we can take in the estimation, that is the h hat. Coming to maximum likelihood function parameters, and also we are taking the some properties for that. One is the consistency, and the next one is the functional invariance, efficiency, second order efficiency after some correction of for basis. We are having the unbiased and also some of the bias techniques, and also we are taking the relation to Bayesian interface, and the next one is some relation to minimizing the pullback Libyer divergence and cross entropy. Here we are having the these are the different properties for the maximum likelihood estimation. Okay, in the previous session also we discussed about these properties, and also we are given some brief discussion about all the properties of likelihood function and maximum likelihood function in the previous sessions. Once go through the previous session, then you can understand these properties, what are the functionalities of these properties in the likelihood function and also maximum likelihood function. Coming to some wireless communication system. Okay, in the wireless communication system we are having some of the propagation. What is the propagation? The whatever transmitted signal from the transmitter to receiver. Okay, from the transmitter to receiver we are having some of the some propagation models. There we having that some line of sight and non-line of sight, LOS and non-LOS. We are having the two different propagations in between the transmitter and receiver. Coming to line of sight means, for example, here this is a transmitter and this is a receiver. Okay, in between the transmitter and receiver there is no obstacle. The signal is in the single direct path. Then this is called line of sight propagation. Coming to non-line of sight propagation means like that you can consider here we having the transmitter and also here we having the receiver. In between, okay, in between transmitter we are having some building or hill or mountain. Okay, there is some disturbance will be occur, then what will happen, it touches to the corner of this uh, obstacle and then we can transmit it to the receiver section. This is come to non-line of sight. Okay, that is a line of sight and this one is a non-line of sight. Coming to here, whatever propagation from the transmitter to receiver signal, we are having that some of the causes in between the transmitter and receiver, we having some propagation causes will be there. Then we have to remove the those interference. For that we are having the equalization, diversity and channel coding. Okay, then use of these we can improve the signal quality. Okay, that improve the some power capacity also in this wireless channel estimation. Okay, further we are considering the equalization, diversity and coding. Okay, why we are go for the equalization means the equalization, it compares the inter-symbol interference. It compares the inter-symbol interference. Okay, in the propagation in between the transmitter and receiver, for example, you are considering the multiple inputs and multiple outputs. Then we are having the in the transmitter side we are having the different antennas. Okay, having the multiple antennas. Coming to receiver side also we are having the multiple antennas for the receiving antennas. What will happen here, we can generate the signals transmit simultaneously. Okay, then what will happen in between the when in between the transmitter and receiver we are generating the multiple signals to the receiver section. Then that time the interference will be occur in between the all the signals. Then we can remove those interference, we can taken by the equalization. Okay, it created the multipath within the time dispersive channels. Coming to coherence bandwidth of the radio channel, intersymbol interference occurs and also we are taking some modulation pulses are spread in time. Okay, then we can go for the equalization. Okay, then we can go for the equalization. Coming to diversity, what will happen in the diversity? In the diversity we are having the some fading. Okay, it overcome by the fading. We are choosing the diversity techniques. There we have the different diversity techniques. One is frequency diversity, time diversity, some spatial diversities, antenna diversities. Okay, those we are discussed in that wireless communication network. Here we can see the what are the fading, what are the different types of fading, what are the how we can overcome by the diversity. Okay, that we'll see into the this session. Coming to an equalizer within a receiver and it compensates the average range of the expected channel and amplitude and any delay characteristics. Okay, that we can go with the equalization. Coming to any adaptive taking, in that one mainly we are taking the adaptive equalizers. Adaptive equalizers we are considering here. Okay, in the adaptive equalizer we are having the training and tracking. Training and next one is the tracking. We go for the these adaptive equalizers. In that mainly we are adding some basic communication diagram. Based on that we go for the equalization. Okay, sometimes we can add some added noise. Okay, and also we can take in the estimation of the signals. Then we can go with the delay of the function in that equalization. Okay, this is the generally known as the time varying or also equalization. Okay, coming to another technique. Actually, in the wireless communication, in coming to propagation, we are having the three different types of techniques. One is the equalization, diversity, and coding. The second one is the coding. Second one is the diversity. What is the diversity? It is a compensate for the fading channel impairments. Okay, for that we are go for this diversity techniques, and also it is implemented by using two or more receiving antennas. Okay, when it is occur, when it is needed. Okay, coming to interference of the signals, we will go for the equalization. But coming to fading, we are having the large scale fading and small scale fading. Both fading will be occur for in the fading. Okay, if you are considering the large scale fading, this is the large scale fading. In between the here we consider a large time interval. Okay, here we consider the a large time interval. Coming to small scale fading means here there is no short. Here we have the only short time interval. Okay, in this one we are having the large distance in between the signals in the time interval, long time interval. Here we having the short time interval. Okay, this is the difference between the large scale fading and small scale fading. In that also we are having the different techniques. Okay, in that also we are having the different techniques. We are having the slow fading, fast fading. Okay, coming to some adaptive selective fading also will be there. With the equalizer, we can quality of mobile communication link is improved without increasing the transmitted power or bandwidth. Okay, if we go the increase the power or bandwidth, okay, sometimes we can improve the some links of the communication. Okay, but then we can improve the signal quality and also increasing the bandwidth or transmit power we can increase. Okay, but without those transmitted power or increasing the bandwidth, we can go with the equalization, diversity and coding. We can also improve the quality of the mobile communication. Okay, we can also improve the quality of the mobile communication links, okay, without any increasing the transmitter power or also bandwidth. Okay, coming to equalization counter, that affects the time dispersion, that is intersymbol interference, ISI. Diversity usually employed reduce the depth and duration of the fades experienced by the receiver, and it comes under the flat fading channel. It comes under the flat fading channel. It is also called narrow band. Okay, see here in this one mainly we are taking the diversity technique for the reducing the fading, whatever experienced by the signal. Okay, coming to diversity techniques can be employed at both base station and also we are taking the receiver section also, base station and also receiver section. The most common diversity technique is called spatial diversity. We are having the different types of diversity techniques, but here we consider the spatial diversity. The most we are using this spatial diversity where you are taken the multiple antennas are strategically spaced on one and connected to a common receiving system. Okay, then we can go for these diversity techniques. Coming to taking the any signal, that is a one signal, it is a null, then you can consider the one or other small antennas mean, then what will happen, the signal will having the high range, that is also it takes the peak. Coming to if you are only one signal you go for the transmitting to receiver, then when any problem will occur the signal will take lost the our information, then we can generate the multiple signals we are taking for that multiple antennas. Okay, coming to the receiver able to select the antenna with best signal at any time. Okay, then we can go for the one or other antennas we can take in, then we can given the best signal at any time. Okay, other diversity techniques include antenna polarization diversity, frequency diversity and time diversity, but the most commonly we are using the spatial diversity. But we are having these techniques, polarization diversity technique and frequency diversity technique and time diversity, but we are most commonly using the spatial diversity. Coming to CDMA, code division multiple access systems often use a rake receiver which provides a link improvement through the time diversity. Okay, it can improve the improvement through the time diversity, that is in the core division multiple access. Coming to channel estimation, okay, up to now we discussed about the wireless system of the link improvement. Okay, for that we are considering the equalization, diversity and also channel coding. Okay, coming to coding, we are having the different correction methods. Okay, for the detecting and the correction methods we are having, there we can use the parity checker. Okay, and the parity, even parity, odd parity and conversion codes and Hamming codes we are considering for the channel coding. Coming to channel estimation, okay, coming to channel estimation, what will happen in between the transmitter and receiver, we are having the some in between the transmitter to receiver we are having the medium, nothing but channel. There we have to estimate the that parameter, that is called channel estimation. Okay, the process we finding the correlation between the array of complex numbers left side and also we are taking the same numbers to the right side, then we can go with the channel estimation. In the wireless communications, the fading is a variance of the attenuation of the signal with a various variables. Okay, we are considering the here variables. What are the variables we are considering here? Time, geographical position, and also radio frequency. We are considering for the different variables in the fading session. Okay, and also fading is often modeled as a random process. Okay, here we taking the multiple samples, that is comes under the random process. Okay, a fading channel is a communication channel that experiences the fading. Okay, here you can see the this is the small scale fading and large scale fading. You can see this red one is the, it represents the large scale fading. The this one is the small scale fading. You can observe here the time interval in between those. We're having the short distance and also we having large distance. Okay, this is the transmitter and receiver in that large scale fading and small scale fading. Okay, coming to small scale fading, what will happen? It will describe the rapid fluctuations. So when it occurs that these small scale fading. Okay, here this is a rapid fluctuation will be there in the small scale fading. Small scale fading. Okay, come to large scale fading. There is no rapid fluctuations in between those samples. Okay, here this is a large scale fading. This is a small scale fading. Large scale fading and small scale fading. Here the consideration of the signal over a short period of time or travel distance, so that the large scale path loss effects maybe it will be ignored for that time. Okay, considering the fading is caused by interference between the two or more versions of the transmitted signal, which are arrive at the receiver slightly in the different times. And also we can take the whenever we generate the multiple signals from the transmitter, then that is called multiple multipath waves. It can combine the receiver antenna and to give resultant signal which can vary widely amplitude and phase. Okay, here we take in the amplitude and phase depending on the distribution. We have the intensity and relative propagation time of the waves, and we take in the some bandwidth of the transmitted signal. Okay, then we can go for the wireless fading channel estimation in the diversity techniques. Okay, coming to diversity, how it can generate in the small scale fading and large scale fading. For that we are having the some important effects. First of all, we have to see the rapid changes in the signal strength over a small travel distance or a small time interval. We can consider the some frequency modulation also. Due to the frequency modulation, we are having some Doppler shifts and different multipath signals. And also we can consider time dispersion caused by a multiple propagation delay. These are the three are most affected for the small scale fading. These are the some parameters we can consider for the small scale fading. And coming to shadow fading, it is comes under the some practically we taken the rain, then from obstacles affecting the wave propagation, and also we taken sometimes that is called shadow fading. Okay, coming to any fading, you can take in the some due to the multipath propagation, and also we can take in the some multipath induced for fading. Okay, those all also comes under the shadow fading. Now you can see the multipath fading in this one. You can see the diagram. You can understand easily. Here we having the this is a base station. From the base station, we're having the three paths here. Okay, the path 1, path 2, and path 3. Here we're having the three paths. This is called multipath fading. Sorry, in this in between the transmitter and receiver, we having some multipath propagation. Then we can get the multipath fading. Okay, it is also it can take in the abstracts in between the base station to receiver. Then we having some fading will be occur, otherwise we can occur the intersymbol interference. Then we can discuss all the multipath fading effects, then reception of the signal in a code division multiple access. Now coming to types of the fadings, here we are considering the slow and fast fading. Mainly we are considering the slow and fast fading. It is a rate at which the magnitude and change are imposed by the channel on the some signal changes. Okay, coming to the coherence time, that we can take and measure the minimum time required for the magnitude change or phase. Okay, here we considering the some changes or phases change the channel become under uncorrelated from its previous values. We are taking some correlation values and uncorrelation values also. Then we can take in from the previous value. And coming to slow fading, mainly there we are discussed about the shadow fading, and also we are having the fast fading. What will happen when it occurs? When the coherence time of the channel is small relative to the delay requirement of the application, then the fast fading will be occur. Here we can change the amplitude and phase, that both are amplitude and phase imposed by the channel varies and considerably over the period of use. This is in the fast fading. Okay, coming to in the fast fading, we are taking the transmitter maybe advantage of the variations in the channel conditions using the time divers to help to increase the some good communication to the temporary fade. Okay, this is in the correcting phase, and we are considering the Doppler shift also we taken in the previous sessions. Coming to mainly those are in the channel estimation. Okay, in the channel estimation, what will happen? We are taking the channel coefficient and also received coefficient. Sorry, received pilot symbols and transferred point symbol. In between those, we are taking the some channel estimation. Okay, for that we are taking the likelihood function in the previous class, but now we are finding the maximum likelihood function. For that, I can recall this. We know it from the this h hat. This we can recall this one, h hat equal to x transpose y bar vectors, okay, by x transpose and x bar. This is we are taking from the previous session, that is in the maximum likelihood function. There we are derived this equation. Then we can write the some vectors of the received observation of the observation parameter. Then we can write y of 1, y of 2, and so on, y of n. Okay, these are the observation vectors. Y bar is the observation vectors. Observation vector. And also coming to pilot symbols. What's the pilot symbol? That is a transmitted pilot symbol. That is also we can have the symbols. That is we represent with the x bar. That we can represent with the x bar. Then what we have to write here? X of 1, x of 2, so on up to x of n. Okay, this is comes under the pilot symbol vectors. Okay, this is all are mainly we discussed in the maximum likelihood function. Here, first of all, we have to derive for the likelihood function. Then we can maximize those parameters. Then the maximum likelihood estimation will come. Okay, this is the pilot symbol vector. Okay, for that we have the same. Just I wrote this one. Then we can write the x transpose this one and x bar. Sorry, x bar. Then we can write x of 1, x of 2, up to x of n. And also we can, that is a transpose. Then we can write x of 1, x bar, this one, x of 2 up to x of n. Then we get the equation. Then we can write x square 1 plus x square of 2 plus 1 x square of n. Then we can write here x square x bar mod square. Okay, then we can write this one. Then from this equation we can write the simplification, that is a summation k equal to 1 to n. We can write x square of r. Okay, that is in the this is from the previous session. There we already simplified this one. Here we can write we can also write x bar square. Okay, we can write this one. Then we can write the estimation of h hat equal to x transpose y bar by x transpose y x bar. Then we can also write this x transpose y bar. Then we can write from the previous one, we can write this one x bar whole square. We can write like this. Then we can take the input and output model. Input and output model. Here we are considering the both models. We are considering the input and output model. Then we can write y of 1 equal to x of 1 plus. For example, if you go for the one observation model, we are taking this one y of k equal to h of x of k plus v of k. This is for one observation model. but here we considering the different pilot symbols in the transmitter section and receiver section. That's why I can write the multiple observation models x of h of x of 1 plus v of 1. Next we can write y of 2 equal to h of x of 2 plus v of 2. So here we can write x of y of n equal to h of x of n plus v of n. Okay, right, like that we can write here. This is a observation vector y of bar. Here we can write the x bar. This is a pilot symbol vector. This is a nice vector. This is a nice vector. We can write like this. Okay, this is a nice vector. Okay, here we can find out the, first of all we wrote the y bar and x bar, then we can simplify the h hat, then we can substitute the value in the x bar vector, then we can write the input and output model. From this one we can write y bar equal to x bar h plus v bar vector. Okay, and here we can take the each of the v of k, the nice each v of k, those are v1 v2 up to so of v of n, those are called independent identical distribution. Like that here we can consider the IID Gaussian. Okay, here we consider the IID Gaussians, that is a independent identical distributions, and we are having the, we also find out the script en, that is a nice and the mean and variance. This is a mean and this is a variance. This is also we find out in the first session, variance. Okay, that is for the noise. Coming to here we can write the estimation of v of k equal to 0, and also same thing I can express the expression I can give here, v of k, v square of k equal to sigma square. We wrote like this. Then we can write individually. Then we can write, for example, you are taking the two identical noise. Then we can write v of k into v of k till equal to, we can write this one v of k and estimation of the v of k till, like this we can write. Then this is 0, because how we can take in 0, that mean is a 0 value here. Then that's why considering the mean value is 0. Then from this one we can write then all the noise factors, estimation of the v of 1, v of 2 and v of 3 up to so on v of n. What will happen here, we can write the all the values in the we can take in the individual estimations. Then we can write estimation of the v of 1, estimation of the v of 2 and so on, estimation of the v of n. Okay, those all are 0 because every factor is 0. That means we having the estimation of the v equal to 0. We know that this is a mean value. From this one we can write some covariance. Okay, covariance we can find out here, covariance. Then we can write v equal to estimation of the v bar and v transpose. Okay, then we can write this one. Then we can simplify these covariance, estimation of the v of 1, v of 2 and up to v of n. Okay, this is in the vector v, the noise vector. Okay, from the we know it, v bar equal to noise vector equal to v of 1, v of 2 up to so on v of n. Okay, from in this we can write like this, and also we transpose here v of 1, v of 2, vector transpose v of 3 up to so on v of n. Okay, like that we can write. Then we can write the estimation v square of 1, v1, v2, and also we can write like this. Here we can having the diagonal v square of 2 and v square of n, so on. Okay, in between we are having the, here we can write v2 of 1, v1. Okay, like this we can write, simplify the this vector and vector transpose of the estimation. Then we can write the diagonally mainly sigma square, the remaining value is 0, because these from the here we having the this value, then we can get the 0. Okay, that is a v of 1 into v of 2 equal to 0. The estimation of the v1, v of 1 and v of 2 are v of 2 or v of 3, then we can get the 0. From this one we can write like this. That is a sigma square, v square of 1 equal to sigma square. We know it, estimation of the v of k equal to, or v of tiddle, another factor equal to also 0, but is the estimation of the v square of k equal to, we can write sigma square. From those two we can simplify this one, sigma square into 0, 0 0 0 sigma square 0 and 0 0 sigma square, like that. Here we have the different, then we can write this is the identical matrix, then we can write sigma square I. Okay, from in this one we can write the sigma square I, like that. We can taking the some properties of the maximum likelihood channel estimation, Okay, for that I can again recall the y bar vector, that is the observation vector, and x bar plus h, the pilot symbols vector, and estimation plus v bar. This is a nice. Then I can substitute this value into our marginal factor h hat equal to x transpose vector and y vector, and we can write this whole square. Then here I substitute these y bar here, then we can also write x transpose, okay, by square. Okay, then we can substitute this were in the y vector x bar h plus v bar. Okay, I can write like this. Then I can simplify this one, x transpose and x bar. From this one, okay, from this one we can write h by, for the both the case we can write x transpose and we taken v bar. Then I multiply this one to this value and this value, then I can write like this. Okay, the same thing will be happen. Okay, from these two I can multiply with the x bar, x vector transpose, then we can get this one. Then from this one we can write the h hat equal to this is a value of the h plus x transpose v bar by whole square. Then we can estimate this. This is the only h hat. Okay, we have to estimate this parameter. For that we can write estimation of the h hat equal to estimation of the h plus x x vector transpose v vector by x bar mod x bar square. Okay, from in this one we can take an estimation. Okay, for that we are considering the h plus, the constant we are taking h plus estimation of the, I can separate this value. Okay, from in this one we can write this one as h and this is the estimation of the remaining one. Okay, estimation of the remaining one. Then I can write here x vector transpose v vector by mod x vector whole square. Okay, this one here we can write the estimation. From in this one we can write h plus x transpose and estimation of the v vector by x vector mod x vector whole square equal to 0. We can write also this one. Okay, from in this one estimation of the h hat and h plus 0. This is a unbiased condition. We know it in the previous session also. What is a unbiased condition? Means we are taking the true parameter equal to unknown parameter or estimated parameter. Okay, further we are considering the true parameter equal to estimated parameter, that is the h hat equal to h. Okay, from this condition is called unbiased condition. From here also same thing. And we can write h hat equal to h plus x vector x transpose and v bar by mod x vector whole square. Okay, here in this one we can take into some variance. Okay, yeah, from that we can write the variance h hat minus h equal to, we can write the remaining one x transpose vector and v vector by mod x vector whole square. Okay, from in this one we are considering the variance. This is a variance. We can write the variance. Okay, from this one we can write E estimation of vector equal to h hat minus estimation here. It's for estimation of the variance. Then we can write the estimation of the this value x transpose x vector transpose and v bar by mod x minus x vector whole square. Okay, this is from the estimation. Here we can find out the estimation. Okay, from in this one we can write also estimation of the two factors. What is that estimation? Two factors, h hat minus h whole square. We can write what is how we can write estimation of the v square of k equal to we are having the sigma square, like that we are having here h hat minus h. Okay, then I can take in the variance, that is a h hat minus h whole square. From in this one we can write what is a h hat minus h whole square, x transpose and v bar by mod x vector whole square. This is the h hat minus and again write h v transpose by v bar by x bar whole square, like that we can write in the estimation. Okay, from that I considering the x bar whole power of 4 estimation of the remaining one. What is the remaining one? X transpose v bar into v transpose, sorry, we can write v transpose and x bar. We can write like this. Then we can write simplify 1 by, sorry, here the transpose 4 estimation of the, sorry, here I consider common the x this one and I can write from this one, sorry, here I can write v transpose into x bar. Then we can write here estimation of the v bar transpose. Here we having that this one by, this is called, we know from previous one what is that variance. We can write the sigma square into identical matrix. Then we can write here substitute sigma square I. Then I can write this one under root, sorry, 1 by x bar whole to power of 4 x transpose estimation of the this sigma square I. Okay, here I can write sigma square I means this value is the sigma square I, this value is the sigma square y. Then total we can write the sigma square bar whole square by mod x bar whole power of 4. This is our required variance. Okay, this is our required variance. We can write also this one finally sigma square by mod whole square x bar whole square. This is our coming to maximum likelihood variance. Okay, we are taking in that maximum likelihood variance and also the mean values for the wireless fading channel of the pilot symbols. Coming to in this one mainly considering the some of the coefficient of the wireless communication system, and also we can take in the some consideration of the maximum likelihood estimation of the coefficient. Mainly here we considering that these estimations, what is the estimation here? We having the variance by sigma square by whole square. This is we are required variance in the coming to this maximum likelihood estimation. Here h is dependent as the coefficient and also we are having the h hat. Okay, basically we are deriving the covariance. Okay, for that we are having the variance. Mainly we are taking the estimation of the h hat minus h whole square. Okay, how we can take in this one? You can we know that we estimate the estimation of v square k equal to sigma square from same as we are taking here, and estimation equal to h. Then we can take in the true unknown parameter and channel coefficient. Furtherly, we are taking the some total energy and also pilot signals, and therefore we are taking the variance of the decreasing with increasing of the energy of the pilot signal of the pilot vector. Okay, and so in the next session we are also taking the some Kramer Bohr, some basic techniques of that wireless fading channel estimation. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.